Got my lemonade going. Okay. All right, should be good to start soon. Let me write it down. All right, so we're going to call this Introduction to Probability. Really, maybe I should have just left it at that, but I kind of wanted to emphasize the random processes part because a lot of the times these probabilities show up in some sort of thing that's evolving in time, such as like, you have a temperature throughout the day that might be randomly changing, or stock price, or basically anything that you can quantify in nature or in any type of natural system. It's usually not going to be um, some definite function that's always some value at some time. Usually it changes randomly, and there's some distribution of values that we think that it could be, and that's what we want to describe basically. So introduction to probability. And maybe I'll put in parentheses and random processes. Okay. Yes, of course you can annoy me. Is that a real question? Right. So yeah, like I was saying, the most obvious ones in nature, well, if you want to call it nature, if you include humans, would be like, stock prices or the temperature throughout the day at a given point of the year. I'm sure maybe you guys can come up with a lot of other ones, but a lot of them involve money, of course. People want to know, how much percent return can I get on a certain bet, and everybody wants to, risk a certain amount of money based on how much they perceive the risk is. So a lot of this has to do with money, but it could be wind directions. You could have random vectors, like on Earth you have wind blowing around randomly for the most part. So I guess mathematicians sort of don't really deal with what is random, quote unquote, because it's sort of hard to say what randomness really is. It's first you have to kind of set some physical laws first, and then you could say, like in quantum mechanics, for instance, things are like fundamentally random. There's like, you know, it's some essential feature. It's not just that we don't have enough information about the process. It's just that it's just fundamentally random. So yeah, the math part sort of ignores that. The math part just says, okay, we have some sample space, some things that could possibly happen, and we assign them some numbers that need to add up to 1, and that's basically all that we need for probability in terms of math. So is temperature really random? Yeah. So I mean that's kind of exactly what I was just saying. So is temperature really random though? It's a question from the chat, and yeah, I mean that's more of like a philosophical question, right? Like if you think that everything is deterministic and everything is, somehow one event determines the next event, and everything we're seeing is just some, sequence of causation, then maybe nothing is random, right? So it gets a little bit into philosophy, and that's why I wanted to say that in terms of math, we don't really care about exactly what is random, but we're modeling it with this mathematics. So essentially we say, so a discrete probability distribution is a sample space, finite, I should say. So we'll just define it for a discrete probability distribution. Let's ignore the fact that maybe infinitely many things could happen. Let's just say there's a finite number of things that could happen here. So finite sample space. And we'll usually write this as like, that's what they use in the source that I put in the resources on the Discord. So it's just some finite set of things that basically could happen, but you know, mathematically it's just some set, but you want to think of it as things that could happen. And a function that assigns basically probabilities to each event. P, so it's a function from this set to, I guess we'll do real numbers, such that if I add up all the probabilities, then I get 1. So basically you're just thinking of this as being some set of things that could happen. P is assigning some probability mass to them, sometimes called probability mass function. And it has the property that if I add up all the masses, all the masses add up to 1, essentially. So I'm getting a lot of questions here. What is this? Yeah. I mean, of course, you could say that dice are random, but you know, if you have the philosophy that everything is deterministic, and there, you know, it depends on your philosophy, I guess. Yeah, true randomness. I mean, essentially, it doesn't matter if things are truly random or we just don't have enough information to determine them. The mathematics sort of describes both of them. So if you want to think of something as like, maybe it's not random, but we don't have enough information to like put it into a computer and determine it, like say hitting a billiard ball like really hard against the wall and it just goes crazy. Like in theory, you probably could determine it, but you would need like some really strong computer or something to look, you know, a million years in the future or something to get the full path. So some things are just easier to model as random, even if they aren't actually random. Like maybe stock prices aren't exactly random because you could maybe, if you had all the information in the market, you could maybe determine where the stock is going to go in the next minute or two. But yeah, usually it's just easier if you don't have enough information or your information is not sufficient. It's usually easy to just say, okay, there's some set of things that could happen, and this is my estimate or my weighting of how likely I think each event is, and it has to just add up to 1. So that's basically what this is saying. Yeah, insider trading. Yeah, I mean, yeah, exactly. Like if a stock has somebody that's insider trading on it, I mean, if I know exactly what prices they're going to trade at tomorrow, then it's not really random, right? So although the people from the outside, if they don't know that person is insider trading, then as far as they know, they could still model it as randomness, and maybe their parameters are off on the randomness, but they have some model at least. Right, so just some things that could happen, assign probabilities to them, and the probabilities have to add up to 1. So this is just a function. I guess technically these are not just real numbers, but they're like within 0 to 1. So maybe we need like, yeah, I should change that. More generally, you could have like some, you know, you would have some, maybe some infinite space, and then there's some weird stuff that can happen, but yeah. Here, because we're basically just using the counting measure here, every probability has to be between 0 and 1 because we can't have things that have negative probability, and if something has more than 1, then in this sum it'll already be more than 1. So Yeah. 0, 1. Yeah. Yeah. Yeah, feel free to annoy me. I don't care about the questions. I like the discussion. So like, what's a really simple case? Well, maybe there's only like two things that could happen. Like you flip a coin is usually the metaphor, but really, you could have any set of two elements. And you can assign a probability to one of the events, and then the other probability, they have to add up to 1, so the other probability is determined by the first one. So probably the simplest case, or simplest non-trivial case, I guess, would be you have this set, which is just basically heads or tails, or like I said, it could be any two-element set. It doesn't really matter what you label these things, but because we're gamblers, right? We we always think of coin tosses or something. I guess that's what people used to gamble on a lot back in the day. Everybody's got coins, right? So something easy to gamble on. Also, the thing about the coin is that's not very well, it's kind of interesting. So the coin is perfectly symmetric, right? So you think, well, not exactly, right? Of course, but like you think you can model it as being perfectly symmetric. And so you think that the chance of getting heads, there's no difference between the chance of getting heads or it being on the other sides and you getting tails. And since there's two events, you figure, well, there's got to be 1/2 probability of getting one of them, and the other one has to be the other 1/2 because it has to add up to 1. So you can build these sort of physical objects, and you can reason about them logically and say, like we were talking about a dice before, it has 6 sides, and there's no bias to any side, so it should be about 1/6 probability of hitting any of the sides. Yeah, so there's like a physical way to build objects that can sort of like simulate this randomness. Yeah, coins are not perfectly symmetric, of course. Yeah. So that's another instance where we're sort of I mean, that's actually a good point, though. I mean, it isn't perfectly symmetric, but we can model it as perfectly symmetric, and we figure, okay, we're not very far off. Like, maybe it's actually 0.50012 probability of getting heads, and, or vice versa. But we basically don't lose much information with that error. There obviously is some error. It's not exactly perfectly 1/2, but yeah. So here's kind of your simplest sample space example. You just have two events, and we're gonna assign some probability to one of the events, and the other probability will be 1 minus that. So let's say the probability of heads, we'll just define it to be 0.1. Here, obviously, this one here is not a fair coin, right? Because the probability of heads and tails is different. But again, like I said, just pretend these are some symbols. I guess heads or tails is kind of annoying, but they actually use this in the Shreve book too, where they're basically flipping coins, but the probabilities don't have to be 50-50. Of course, you could flip, I guess, oh no, you can't do that. No, never mind. Could you compute the kurtosis of the normal distribution? We could do that. I didn't really prepare it, so I'd probably have to write it down or look it up. We could probably try to figure that out. Maybe that would be better to do tomorrow, though, when we do some exercises. Yeah, kurtosis. It's actually annoying. Kurtosis is usually the fourth moment, but I think sometimes they use sometimes there's a central. I know there's like two different forms of kurtosis. I can't remember what the difference was. Some scaling factor or something, but yeah, it's the fourth moment. I remember that, but I think there was some issue with. Oh yeah, there's central moments versus just regular moments, so that's also annoying. Yeah, the skew is 0 for normal. Yeah, that's true. Um, let's see. Yeah. So then a common thing is you have this probability distribution with this sample space, and you want to assign some values to the different events. So this could be like in the event of heads, maybe, well, so the example I came up with was, let's say I play a chess tournament and I have a 10% chance of winning. So in the probability of H, you could think of as H is like I win the chess tournament. Tourney. And T could be lose. Right, so let's say like I play a chess tournament every week, or here's kind of like the outline of the problem. So let's say I play a chess tournament every week. Once per week. With 10% chance of winning. And let's say if I win the tournament, then let's say it's like a sponsored tournament or something. If I win the tournament, I win $100, and if I lose, well, I didn't have to pay money to join, so I just win $0. So let's say, so usually like I was saying, usually the setup is you have some sample space with a probability distribution, and then you want to assign values in the event of either event happening. So in this case, we're going to say, if I win the chess tournament, I win $100. So I win $100. And tails means I win nothing. Okay, so this is like a binary event. Either I win 10% chance I win $100, or 90% chance I win $0 and I go home sad. But I play every week, so we want to know. Let's say I play. Well, I'll get to that in a second. But this is basically the setup. Oh, what, the board squeaking? Was that the ASMR? Yeah, of course, this is just I'm simplifying things here. Of course, we can always make it more complicated by, adding if I if I lost, obviously I'm investing some amount of time or gas or something. But I'm just picking these numbers just to simplify things a little bit, because every time so we're going to, basically the idea of the problem is, if we go to play chess every week, let's say we play 50 times in a year, we take two weeks off or something. So each time I play the tournament, either I win and I win $100, or I lose and I have the same amount of money the next time. So if I play 50 times, essentially, you could think about this as a random process. So, each time there's two possible things that could happen. In the end, So actually, well, yeah, there's two possible things that could happen, but yeah, the amount of values that it can take in the end is actually not too many, because either I keep the same value or I go up 100 each time. So yeah, there's only basically 50 times 100, or 51 times 100 possible outcomes. Either I win 0 times, 1 time, 2 times, 3 times, all the way up to 50. Do online gambling, yeah. I mean, all the math here is basically applicable to any type of gambling, or, yeah. Wait, so you're ignoring order. Well, here, because addition is commutative, the order that I win doesn't matter, right? Because I win $100 every time. So yeah, actually that's a good point. Yeah, so the order actually doesn't matter. I could win, let's say I win 5 tournaments. It could be the first 5 I play and then I lose the last 45. Or I could win the first one, the fourth one, the 7th one, the 10th one, and the 11th one, and then lose all the other ones, or etc. Right? So, yeah. Yeah, let's just make it simple. Let's say that, yeah, you can't draw the tournament. Yeah, you either win the tournament or you lose. Yeah, it's a binary event. Yeah, so we're looking at the total winning, not win-lose order. Of course, yeah, I mean, that would be a different random process. Of course, you could try to... Let's just assume that every tournament is independent of the next one, so the probabilities don't change. But of course, in real life, that might not be true, right? Because you might lose a couple tournaments and then get down on yourself, and then the next tournaments you might have even less chance, or you could be the opposite where you lose a couple tournaments and then you get really angry, so then you try really hard and then you have a higher probability the next time. So let's get rid of that complication, and let's just say every tournament doesn't affect the next one, so every tournament is independent. That's a notion in probability. If every event, the next event has nothing to do with the previous events. So let's just say every event has this same fixed probability of events, and I can either win every one or lose every one, and it's just random. So it could be one or it could be the other, but they have these probabilities. 10% win chance, 90% lose. Yeah. So that's the first thing we want to know. So one notion of, average, or how much you expect to gain per tournament, is the notion of expected value. So for this problem, if I have a 90% chance of losing or making no money, and a 10% chance of making $100, if I play 10 times, I can expect to win 9 of them and win 1 of them and lose 9 of them. And in that case, I would have $100, and I played 10 times. So you could see how the average would be $10, right? Yeah. But basically, to calculate the average, what we're going to do is take the probability of each event and multiply it with the what the value is associated with that event, or how much we're going to end up, in this case, how much money we're going to end up with if that event happens. So essentially, the average or the mean here is just going to be this probability, 0.1 times 100, because I win $100 in this event with this probability, and I would plus $0 times this 90%. So it's just going to be 0.1 times 100, which is just 10. So that means that on average, I should expect to win about $10 per tournament. So if I play 100 tournaments, I should win 10 times 100. Or if I just play 10 tournaments, I should win $10 times 10. Okay, so let's just write down again what I just said. Okay, so the mean, so a lot of the times you'll see it like this: expected value of a random variable x. This is the sum over the things in x. So each event, I sum over the events that can happen. Basically, the value of that event times the probability that that event happens. And then I add all of those up. So for the example we were just looking at, there's only 2 events, so there's only 2 elements in the index, the sum. And so the mean for us was, well, you could either get the value of 0 with probability 90%, or you could get the value 100 with probability 0.1. So this is just 10. Yeah, all sums are just integrals in disguise. Yeah, I said that to Zach the other day, yeah. Yeah, you can view all of these sums as Lebesgue integrals, but we're always just using the counting measure, and that just means that every event has, well, actually, I guess it's technically like the uniform probability distribution. Yeah, good question. So what about multiplication? Oh, you're saying what about multiplication for integrals? Yeah, no, I mean, well, multiplication is just not an integral, right? So integrals are linear, right? That's the whole. We'll actually be sort of using that. So integrals are linear, and thus expected value is also linear. So yeah, just real quick aside, we do have the property that expected value of a constant times x plus another constant is just c times the expected value of x plus d. So expected value and integrals in general are linear. Which sort of, well, yeah, okay, we'll just leave it at that. Yeah, so multiplication and power, well, so, I mean, actually, yeah, that's a really good question. So it's linear in this sense. What do we think do we think the expected value of the log of x is equal to the log of the expected value of x? Let's say everything's positive. This question mark. So, yeah, we can pull constants out. We can pull sum of a constant out. But can we pull a log out? So log expected value, I take the log of all the values that I get versus I take the log and I take the expected value first. E to the integral log f of x. Yeah, so Jeff, you said what about e expected value of x times expected value of y? Yeah, if x and y are independent, then the product, I was just looking at that in the book actually, yeah. The product does multiply if they're independent, but if they're not independent, then it's not true. Yeah, Black-Scholes, that's actually where you're getting way ahead of me, Jeff. Yeah, you're skipping to the last page. Well, actually, we'll probably do that maybe Friday or at least mention it, but right. So the fact is that this is not true. So expected value is linear and log is very much not linear. It's very concave down, right? So every line forms like a secant where the log is actually above the secant line, right? Well, every line that passes through 2 points. Of course, not the tangent line. But yeah, because of this concavity of log, the expected value of log of x is actually always, am I saying this right? Which one's less? Yeah, so which one is less than the other one? I should know this. What did I have here? Yeah, okay. Right, I wrote it the same way, okay. So basically, like, this log sort of doesn't behave well with expected value. It's sort of, when I take a log of a variable, it actually lowers the expected value than if I just took the log of that expected value first. So this is actually not, there's no equality here. This is actually, it's usually less, but I think maybe they could be equal. Yeah. But it's always less than or equal to. I guess maybe if x only takes on one value, then they're technically equal, but yeah, so basically the concavity of this log gives you an inequality here. And I think there's a general formula for the concavity here with the expected value. I can't remember the name of the theorem. Maybe somebody in the chat could tell me. I'm trying to remember. I know it's a name of some guy. It starts with an S maybe. Yeah, so you can actually replace log with any concave down function, so where the second derivative is always negative, and this will still be true, so this will be less than or equal to this. You just replace ln with f. Or if you have a concave up function, then it's the inequality is the other way. So you could actually take like the exponential of x, and then you'll get greater than or equal to the exponential of the expected value of x. So yeah, I can't remember the name of that, but yeah, there's a name of a famous theorem that talks about the relationship between concavity and the expected value. Yeah, Jensen's inequality. There it is. Okay, it wasn't a Jensen. Yep. It's Jensen. Yeah, I think the formal statement is you have an f here instead of ln, and if f has negative concavity, then you have this inequality this way. If this function has positive concavity, then you have the inequality the other way. I'm not exactly sure how I would prove that. We could go into it more probably another day if people are interested, but yeah, there it is in the chat. Pretty interesting formula. I mean, this does come up in your Black-Scholes stuff we were just discussing, and actually stuff we'll probably get into like Wednesday, Friday. Right. Let's talk a little bit more before I get to that stuff though. Right, so we have this binary event, either it happens or it doesn't happen. Say if I win a chess tournament, I win $100. If I lose, I just win nothing. And now let's say I go to these chess tournaments every week. I play 50 tournaments in a year. And yeah, so now I want to know at the end of the year, we have a possibility. There's a lot of different possibilities. Like I could win every tournament, I could lose every tournament, I could win just 2 of them and lose all the rest. And in fact, there's everything in between, right? So I could win any number between 0 and 50 of them, and I'll lose the complementary amount, right? So yeah, we can talk about adding independent events of these binary events. So each one of these I can call some xi, and we could talk about what's the distribution of the sum of all of these. So what happens at the end of the year when I play 50 different chess tournaments. So let's look at a new x, which is just x1 plus x2, and I do it 50 times, where each xi is some chess tournament. And again, we're just assuming that each tournament is independent of the next, so the probabilities, it's just a binary event every time, and the probabilities don't change based on what happened in the previous ones. Yeah, binomial. Yeah, so this you could call this, well, this is the distribution, but the process from like time 1 to time 2 to time 3, that you could call that an arithmetic binomial process. Okay, because basically we have, this binary event, either it happens or it doesn't happen, and we're just doing it over and over again, basically. And what we're doing is we're adding the results, so I'll call it arithmetic, and I want to differentiate the arithmetic part from a different type of series where we could multiply the randomness. So that would be some notion of like a geometric binomial process, which is where we're going with Black-Scholes and stocks and stuff. A stock will change from one time to the next. It will change like geometrically, meaning that it's proportional to the price of the stock. This is not that though. This is just saying we're going to go up, either up 100 or up 0, and it doesn't matter how much, what the value is. We're just doing that every time. So there's arithmetic binomial processes, and there's also geometric binomial processes, which would be closer to like a stock price. So this is like something a little bit simpler. Get rid of that. So yeah, so oh, ads are coming. Oops, sorry. Didn't see that. Okay, yeah, well, we didn't really do much. So I was just saying, we have this event where we're going to each tournament every week. We go to 50 tournaments just to make it simple, just to keep the numbers easy. And every event is independent of the next. We could, lose 10 in a row and then win the next 10. It doesn't really, anything's possible, right? Well, not anything, just there's only certain events that are possible, obviously. So, yeah, so what's a possible sequence of events? We could look at this process over time, over the 50 weeks. So let's say this is 25 weeks in the middle. And we start out at $0, and maybe like this is, I don't know, $7,000 or something up here. And as we go, we either win the tournament or we don't win anything. And it could just look like something like that. So maybe we just win like, I don't know, maybe like 1, 2, 3 tournaments throughout the year or something. But if we ran this year over and over again, like a billion times, you could, we're going to have some sequence of events. We might get another sequence that looks slightly different. Maybe it goes here. But if we view all of these like a million times, there's going to end up being some distribution of possible values. And that distribution is actually going to look somewhat normal. It's going to look something like, not exactly normal, but as this number of weeks goes to infinity, it will get closer and closer to being normal. Yeah, exactly, Jeff. Yeah. That's exactly the point. Yeah. So if you go up 10% and then down 10%, you're not exactly where you were to begin with. So that's the key difference. If I go up, if I go up by $10 and I go down by $10, then I am where I started. But if I go up 10% of my value and then I go down 10%, I'm no longer where I started. Yeah, it's normal approximation to the binomial distribution, yeah. Right, so we can actually calculate the value. So let's look at all the possible values that this could take on. So, we're playing 50 times. So either we lose all of them and we make $0, we win all of them, we win $5,000, or we win any multiple of 100 in between those, right? So I don't want to write down the formula for all of them, but let's just do one possible, or actually, yeah. Right, so let's look at the total sample space here. So now this new sample space of this process, this sum, is either I can make $0, $100, $200, all the way up to 5,000. And let's not write the general formula, but let's just check what's the probability of getting one of these events. Well, let's check what's the probability of getting like $500 exactly. So in order to get $500 exactly, like we were saying before, we would have to win 5 of these. So either I win the first 5, lose the last 45, or I win the first 45, lose the first 45, win the last 5, or any kind of combination in between. All I have to do is I have to win 5 of them at some point, and then I know I lost the other 45. So essentially the probability of getting exactly $500 would be it's the probability of winning to the 5th power, the probability of losing to the 45th power, and then how many different ways is there to do that? Well, I need to, out of the 50, I need to choose 5 of them to win. So it's just 50 choose 5, which is this combinatorial number, right? This is like you have 50 possible things. I need to choose 5 of them, but I don't care what the, which 5 it is. It's just some 5 of them. How many different ways can I do that? 50 choose 5. Right, so and then so P here is the probability of winning, so it's 10%, and Q is the probability of losing, that's 90%. And if I did this out on the calculator, I got about 18.49%. Oops. Just circle that. Okay, so guys, what's the reason I picked 500 here? What is 500 in this distribution? I guess maybe I should write exactly just to remind you. So we have 0.1% chance, or sorry, 10% chance to win $100 and a 90% chance to win nothing. We said the mean of each event was 50. So what is 500? Or sorry, was 10, I mean? Yeah, it's also the most, that's what I was getting at. So each one, remember the average or the expected value is how much I can expect to win per event happening. If the event happens 50 times, I can expect to win 50 times the average. So if the average is 10, we play 50 times, then 500 should be the sort of the average, and I think in this case it is also the mode. So it's the most likely outcome. And in this case, it's only 18%. So even though it's the most likely outcome, it still has a less than 1 in 5 chance of happening. So we're actually more likely to not get $500 than to get $500, even though it's the most likely number. It's kind of a weird way to think of it, right? But yeah, it is true. Because, we're also very likely to get $600 or $400, even though it's not as likely as 500. It's still, I think I looked at 400 and it was like 18%, and I looked at 600 and it was like 17.5 or something. So $500 is the average that we should get, and it's the most likely outcome at 18.5%, but it's actually, we're actually more likely to get some other outcome, even though it's the most likely. Right. Yeah, Jeff, you keep repeating, yeah. It's funny. But yeah, that's good. That means, my presentation has logical coherence if you're able to guess what I'm about to say next. So yeah, this is kind of I don't want to say the simplest, I would say the binary setup was the simplest setup, but this is kind of like your simplest random event, right? Where each time you're just adding or subtracting some number, and you're either adding with some probability or you're subtracting with the complementary probability. But essentially you get this sort of zigzag process where it's going up or down each time, and there's no proportionality to the price or anything. So that would be getting into like this geometric random process territory. So we're still dealing with the arithmetic stuff, and the arithmetic stuff, it's easy to calculate this, right? It's just simple like PQ binomial coefficient, and we know each probability. So very simple formula for each one. What did I want to say about this else? I think that's probably it for that. Yeah, and then I just wanted to go back to what we were talking about with the log. So yeah, instead of adding these sort of random changes, you could think of it as what would happen if we multiplied these random disturbances, you could think of it as, or some perturbation some random perturbation where instead of adding each time, it's multiplying by something. So either we're multiplying by something maybe slightly bigger than 1 or something slightly smaller than 1. Yeah, and then in that sense, when the randomness is being multiplied, that's when you're getting into like modeling stock price, right? Because the stock price is going to go up or down randomly each day, and it's going to be proportional to what the stock price is currently. It's basically going to go up or down a random percentage, not a random arithmetic amount like in this case. Okay, so yeah, let's just rewrite this problem now, but instead of us basically gaining $100 or $0 each time, let's assume that like our, think of it as like our bankroll or whatever is going up or down by some percentage randomly. So I'm gonna just rewrite this, instead of a sum, it's gonna become a product. And I just want to make one comment about it, and then we'll talk more about this on Wednesday, and then more on Friday. But yeah, I think this is a whole other thing, so I don't want to get too deep into it. But yeah, this is basically the arithmetic case. We can deal with it with these binomial coefficients pretty simply, but you could think of a generalization of this where instead of adding these random variables, you're multiplying them. Yeah, the log of the price will behave arithmetically. Yeah, you beat me again. So let's look at a geometric version. Okay, so now we're going to define x. It's going to be 1 plus x1, and then just divided by 1,000. Okay, so now this is the same x's that we had before, so now each time we're either going up by 10% or we're staying the same, right? Because x1 is either 100 or 0. So every time we're either multiplying by 1 or we're multiplying by 1.1. Okay, so this is like so multiplicatively random. Random process. And so here though, something interesting happens. So what is the expected value of x? I think Jeff you might have asked this question just before, or you might have answered this before. You were talking about if they're independent, which in this case we're assuming all these changes are independent. So if your random variables are independent, then you can actually just multiply the expected value. So this expected value is just the product over the i's of 1 plus expected value of, yeah. I guess I goes from 1 to 50. So the expected value here actually does multiply. But the difference here now is if we take the log at the end though, so now that means that the log of the expected value of x, well now it's a product of log of a product, so it splits, so it's a sum of the log of 1 plus the expected value of xi But if we take the logs first, then we get something else. So what happens if we take the logs first? Maybe I'll write it in a different color. Yeah, so the log of prices does behave arithmetically. But there is a little bit of a difference. So I want to point out what's the difference between log of the expected value, which we get this, and what happens if I take the log of the variable, which, like you said, behaves arithmetically, and then I take the expected value after. So it's not. I was actually doing this in my head earlier, and I was actually getting a little confused. So, but it is it does work out correctly. So if we take log of x, this is just the log of this, so it's a product, so it's a sum of 1 plus xi over 1,000. Right? But then something weird happened. Oh, I forgot a log. But then something weird happens because when we take the expected value here, what's the question? Expected value log of x equals log 1.1. Yeah, so what's happening here? If we try to take the expected value of this, why is this not equal to this? Right? In fact, I think we said this should be smaller than this. So this means expected value of log of x is, so expected value of this. What we're actually going to have to do is we're going to have to, because this is a random variable xi, if we want to know the expected value, we're going to have to plug in each value here and then multiply it by the probability of each one. So we're actually going to get an even larger sum here. Right? So each one of these terms is actually going to split into two terms, right? Because we have a binary event. Either xi is either 0 or xi is 100, and there's two different probabilities for those. So once we take the expected value, we're actually going to be taking a sum, and we're taking an average over two logs, and the average of the logs is always going to be smaller. Did I have that correct? Yeah. The average of the logs is always going to be smaller than the log of the averages. So that's essentially what's happening here. We're going to get a sum here of a log, but it's going to be a double sum because each of these individual terms is going to end up being a sum of two terms, and each one is going to be multiplied by the probability of each event. Yeah, so that's where Jensen comes in. You can explicitly see Jensen here it's Jensen for a binary event, right? Just that the log of the average, now I'm probably going to mix it up when I say it, but the average of the logs is smaller than the log of the averages, even when you just have two events. And that's probably simpler to prove. That's like a special case of Jensen, right? But yeah, so that's essentially where you're getting this inequality here. Here you're taking averages of logs. Here you're just taking the log of the average. So there's no double sum here. This is just a single sum. Here you actually have a double sum, and each of these individual terms is an average of logs, which is going to be smaller than this value. Okay, so hopefully you followed that. The main point here was that we have these random processes. The simplest case is they're just changing by some binary event. They're either going up or down arithmetically or geometrically. And here we just showed basically Jensen's inequality that for the multiplicative version, the log does behave arithmetically, but the averages don't behave the way you would expect. So the log of the expected value is actually larger in general than the expected value of the log, which is, yeah, so it's a double sum. Yeah, I don't want to write it all in here, but I basically explained it in words. I just don't have enough room. Logs are commonly found in ponds. Yes, that is true. True. Thank you for stopping by the way, Dr. Gold. So yeah, I think that's basically all I have for today. I kind of summed it up, and where we're going with this is we really want to think about these geometrically evolving processes, because these are the ones that are kind of like the most interesting after the arithmetic ones, and also they're, you know, very important for Black-Scholes, stock prices, and basically, you know, in this type of stuff, you have something called a stochastic differential equation. So in regular differential equations, you know, you might have y equals y prime, and the solution is e to the x. So here, this is like a random version of a differential equation, where in the limit you have some sort of differential equation where the randomness is proportional to the price, and then Black-Scholes is basically like your continuous solution for that. So Black-Scholes is basically like if you take the number of these multiplicative events and send them to infinity, and the amount of time between each one is going to 0, that's when you get Black-Scholes. So yeah, I think I'll stop here, and we'll continue like Wednesday and Friday. Wednesday, yeah, let's try to do some more probability exercises. And if we have any linear algebra stuff that hasn't been dealt with, if you guys, you know, have any questions for me, or maybe something from class came up or something, try to put it in the Discord, and we'll tackle them tomorrow. Any I was trying to say untackled. Not sure the word I was looking for there, but okay. Is there anybody streaming right now? Who should we send off the stream to? Let's see. Oh, we got Dawn.
Bill, can I get a shot?
Ah. Let's see. Dawn's doing math, so let's probably send it to Dawn. All right. Thank you, everybody. Thank you for coming. Dawn Factorial. Yeah. Let's go say hi to Dawn.